All right, so the previous lecture was a long one. So we are lucky that it just ended by itself. Now, I will open a new page and I'll try to summarize the things that we have seen. So in short, you are expected to be able to answer this question. If you can expand your signal, periodic signal, into Fourier series coefficients, and if you can locate the frequencies corresponding to that, okay, these may be complex conjugates of one another, or they may be real. If they are complex conjugated, their magnitudes are the same still. So whatever this frequency is, let's say omega 1, this is omega 2, and this is omega 3. Clearly, these are integer multiples of a fundamental frequency. That's a necessary condition, but whatever they are there. They are just the frequencies. So if you can, excuse me, express your signal in terms of these Fourier series coefficients, and if you are given, or if you can develop the formula for h of omega, it may be, I don't know, God knows what it may look like this maybe, okay, just not some arbitrary shape. You just need to multiply this value, let's call that this value is A, with the value of h of omega, sorry, it's not A, this is omega 1. The value of h of omega at omega 1, this value. So A times h of omega 1, for example, will be the Fourier series coefficients of your output. Let's call them dk's. So this will be d1, for example, whatever it is. This, for example, omega 1 and d1. So we will multiply b, the next Fourier series coefficient, the other Fourier series coefficient, with the value at omega 2, which is this value. So b times h of omega 2 will be d2, which will be, I don't know, something like this maybe, d2 at omega 2. Right? This is how we generate d1, this is how we generate d2, and every such Fourier series coefficient will be found in a similar manner. This is at omega 3, for example. So we will multiply this c, the value c, with h of omega 3 to find d3. Something like this maybe, at omega 3. The others will be the same. Here, d minus 1, d minus 2, etc. Something like this. Are you able to do this? You must ask this question to yourself. Do you understand what's going on here? You just need to multiply the Fourier series coefficient with the value of the filter. It may be a low pass filter, band pass filter, or any arbitrary shape filter like this. The rest is, once you have d1, d2, blah, blah, you can just combine them to find y of t. Y of t will be expressed in terms of these Fourier series coefficients and the harmonics at frequencies omega 1, omega 2, omega 3, etc. That's what you are responsible for. But of course, before that or after that, there are some extra things that we will still cover. And now I will again open a new page and show you some examples. All right, this new example. This is a trivial example again. Most of the examples are, as you see, easy examples, but in the examination, the questions suddenly, abruptly become very, very difficult. But that's life. Of course, that's why you need to practice and exercise with the questions from the book and from other resources. In this example, we have a let's say, an indefinitely simple input-output relation of a linear time invariant system. It's this. Y of t is equal to x of t minus 3. It's a delay system. Now, what is the frequency response, for example, for this kind of an input-output relation? How can you find the frequency response of the system? It may be a good idea to apply e to the j omega t as the input. This is x of t. Then y of t will be equal to e to the j omega t minus 3. Right? Simple input-output relation. T is delayed by 3, which is equal to e to the j omega t times e to the minus j 3 omega. Now I'm going to write it like this, e to the minus j 3 omega times e to the j omega t. So notice that this is the same as the inputs. The input was e to the j omega t. The output is also e to the j omega t times this. What is this? It is h of omega. Simple. You found the h of omega. I didn't give you h of omega, but you found it. So you can now use this h of omega to find the response to some sinusoids. This may be a little bit awkward because let me see if I have the continuation of that. Well, it's not even necessary. Let's think of it like this. Suppose that in this question, in this example, a further sub-example we generate as x of t is equal to cosine 2t, a signal. And I'm asking you, what is the output? Of course, we know the output. The question is, y of t is equal to a question mark for this system. Of course, it's easy because we know that that is, let me write it in red, that is equal to cosine 2 in parentheses t minus 3. It's just a delayed version. All right. But now I'm going to solve this question by showing my right ear with my left hand like this. An indirect way of solving the same question for this periodic signal. It is periodic with a fundamental period of 2, and there are only 2 harmonics. One of them is at omega 0, which is 2, and the other one is at minus omega 0. By using the Euler's expansion again, x of t is equal to 1 over 2 e to the j 2t plus 1 over 2 e to the minus j 2t, just using the Euler's expansion. And this is c1, and this is c minus 1, and omega 0 is equal to 2. All right. Now I'm going to use this h of omega, which is e to the minus j3 omega. Let me also write it. H of omega, the frequency response is e to the minus j3 omega. So from this information, can you tell me for y of t consisting of d1, d2, and the same omega 0 is equal to 2, what is d1 and d2? d1 is equal to c1 times h of omega at omega is equal to omega 0, which is 2. What was c1? It's here, it's 1 over 2. What is h of omega at omega is equal to 2? What is h of omega, first of all? H of omega is e to the minus j3 omega. Now, let's substitute omega is equal to 2. That makes e to the minus j times 3 times 2, or e to the minus 6j, or j times 6. Okay, this. And let me also find d2, that is equal to c2 times h of omega at omega is equal to minus 2. It's not d2, of course. I have to put d minus 1. I'm sorry about that. I'm just correcting this. This is d minus 1. There are two Fourier series coefficients, but one is for C1, the other one is for C minus 1, not C2. Sorry about that. Let's correct it. So d minus 1 we are looking for. D minus 1 is h of C minus 1 times h of omega at omega is equal to minus 1 times omega 0, that is minus 2. And C minus 1 is 1 over 2. And h of minus 2 is e to the minus j times 3 times minus 2. That is e to the j6, or 6j. That is d minus 1. So I have d1 and d minus 1. This is d1. This is d minus 1. How can I construct my signal from two Fourier series coefficients? By using, or by summing up the corresponding harmonics. What are they? They are, so y of t is d1 times e to the j2t plus d minus 1 times e to the minus j2t. This is how I'm going to combine these two harmonics, given that 2 is the fundamental frequency, omega 0. So one of them is 1 times omega 0, that is 2. The other one is minus 1 times omega 0, and that is minus 2 for the second harmonic. And that is equal to, in 1 over 2 parentheses, let me put this into a parenthesis because it's common for d1 and d minus 1. I have e to the j2t times e to the minus j6 plus e to the minus j2t times e to the j6. Okay. I just carefully substituted d1 and d2 into their positions, and I get this one. And that is equal to 1 over 2, again in parentheses. Can you hear me from here? Okay. Can you see the screen? Do you see my writings?
Evet hocam, görüyorum.
Okay. Then I will continue this way. There seems to be a bug going on over here. I hope it's still streaming, but no, it's not streaming. Just wait a little bit. Try to connect again. And I don't know why this happens, but you know, there seems to be some problems for internet connection today. It just kicks me out. Are you with me now? Hopefully for the last time I'm asking. Okay, good. Now it's, as you see, it's in the form of e to the j alpha plus e to the minus j alpha over 2. Therefore, it's a cosine of that alpha, and that is cosine 2 t minus 3. So we found it. You remember this answer? It was here, the same. Good for us. It is showing us that the idea or the formulations are correct. But I did this trivial example or useless, unnecessary example to show that you can just multiply the Fourier series coefficients with the corresponding values of h of omega at the corresponding omega frequencies, and you come up with the new Fourier series coefficients. And when you combine those output Fourier series coefficients, you will obtain the output signal y of t. And that's okay, that's nice. But now the next issue is how to find the Fourier series coefficients for a general class of signals. Let's talk a little bit about those. So let me open a new page. Okay. By the way, you must already know this, or I told you already, but it is from this fact that the x conjugate of t is equal to x of t for real signals, that will give you the fact that c of minus k is equal to ck conjugates, saying that the Fourier series coefficients are conjugates symmetric. All right. I didn't do that, but it's a very easy practice. Please do that. Write x of t in the form of the Fourier series coefficient summation, like x of t is equal to k from minus infinity to infinity ck e to the j k omega 0 t. Write it like this, and write the conjugate of this one as well. And you will see that when you take the conjugate, okay, let's do it, because it's not going to cost us a lot of time. X conjugate of t will be k from minus infinity to infinity ck conjugate e to the minus j k omega 0 t. This is how we take the conjugate. The complex or imaginary exponential will become negative imaginary exponential, and ck will become ck conjugate. Now let's say L is equal to minus k. Okay, make this kind of a substitution, and it will be L from again minus infinity to infinity c minus L conjugate e to the j L omega 0 t. And this is equal to, also equal to x of t, telling me that it's k from minus infinity to infinity, ck e to the j k omega 0 t. So at the same k is equal to L value, it tells me that this part and this part must be the same. So it is telling me that C minus K conjugate is equal to CK. I put it in a different format, but actually these two are the same things. Just conjugate both sides of the equation and it will give you C minus K is equal to CK conjugate, because if you conjugate twice, it will give you the same number. So it's not a God-given or any magical thing to say that the Fourier series coefficients are conjugate symmetric, because that's what I told you. Actually, it's very easy to show it. All you have to do is to write this one for real signals. The signal and its conjugate are the same, equate them, and it will automatically give you this property. Okay, now the last thing that we will see for today, and that's a good starting point, is to, so I have to start a new page, is to derive the formula for CK. Okay, that's something critical, and we need to learn how to do that. The result is more important to you than the derivation. The derivation, it's just a theoretical practice, but for good scientists and good engineers, it's always a good idea to know how these are generated. But I'm not going to ask you in any kind of an examination about derive the formula for this Fourier series expression, CK, for a given periodic signal x of t. That's something that I will never ask. You really have to know the formula, the result. But we will do the derivation now. And I suggest that you follow it, because it makes sure that you understand the mathematical definitions and derivations. That's a good thing. So we have this already known formula. This time I'm using a case because I took the notes as a case. It's just the complex Fourier series coefficient. It could be CK. But this is the formula. Now what I will do is a trick to multiply both sides of the equation with another complex exponential in this form. Because when I multiply both sides of the equation with the same thing, the equation stays the same. And it's not a trivial 0 by 0 or times 0 multiplication for both sides. That would be too bad. So this is a non-trivial multiplication, and the expression, the resulting expression, is meaningful. Okay, both sides of the equation are multiplied by e to the minus j n omega 0 t. And now I'm going to integrate both sides of the equation using a definite integral from 0 to capital T. Since the equations, the functions at both sides of the equation are the same, when I integrate with the same limits, since the functions are the same, the integration results will also be the same. And from 0 to t, I say, or within a duration of the period, it could be from minus capital T over 2 to capital T over 2, or 0 from capital T, or from minus capital T to 0. The duration is important here. And of course, T is equal to 2 pi over omega 0 from the previous expressions. X of t e to the minus j n omega 0 t is equal to the integral of the right-hand side from, again, 0 to t, summation k from minus infinity to infinity. Now I'm going to write this as ak times, and I will combine the multiplication exponential terms in the exponent, is going to be like e to the j in parentheses k minus n omega 0 t. Of course, we need a dt here, and we also need a dt here. Okay, in this integration. So left-hand side is still equal to the right-hand side. Okay, now I will do a further trick of interchanging the places of summation and integration. Lots of tricks going on here. AK will be left out of the integral because it has nothing to do with t. Inside it is the t function, e to the j k minus n omega 0 t dt. And the left-hand side is the same integral. Now, here comes the important observation. This thing is an integral of a symmetric sinusoid, of a pure sinusoid. In a duration of 1 period, in 1 period. Now, within 1 period, if you integrate a cosine, but it must be starting from a point and ending at the same point. It must be 1 period. So within 1 period, a cosine integrates to 0. A sine integrates to 0. Any shifted sinusoid integrates to 0 within 1 period. And if k minus n here, for example, is equal to 1, then it means I am integrating a sinusoid within 1 period. If k minus n, this thing, is equal to 2, it means I'm integrating within 2 periods. Okay, inside it, it will be fitting with 2 periods. So when k minus n is 1, it's going to be like integration of this from 0 to capital T. If k minus n is 2, there will be 2 oscillations because the frequency will be twice, so the period will be half. So half of the period will be like this, and then again like this. So what's the integral of the red function? Again 0. If k minus n is equal to 3, then I will have 3 oscillations inside capital T, and its integral will still be 0. So whenever k minus n is something, whenever it is a number, I will come up with this integral 0 to t e to the j k minus n omega 0 t integral will give me 0. So this integration from 0 to t will be equal to 0 for most k minus n. In fact, for almost all of them, except k minus n is equal to 0. When k minus n is equal to 0, it means e to the j 0 omega 0 t, which is e to the 0, which is 1. And what's the integral of 0 to capital T 1? So when k minus n is equal to 0, integral from 0 to t 1 times dt will be equal to capital T. So this integral is capital T only when k minus n is 0 or k is equal to n. Only for k is equal to n or n is equal to k. That integration will be equal to capital T. And that case, let's substitute. Then the left-hand side of the equation, let me write them in green, will be 0 to t, x of t e to the minus j. Now n is equal to k, so let me use k whenever I see n, e to the j k omega 0 t dt. Because for all other n's, all other n values, the right-hand side became 0, because that integration part became 0. This is equal to I think I am writing it a little bit inappropriately. Let me write it as n still, omega 0. Instead of, now at the right-hand side, I will have only one instance of this k summation from -infinity to infinity. When k becomes equal to n, that summation will have a non-zero term. For all other k values, that summation will have 0 contribution. So the right-hand side will be when k is equal to n, a n, and when k is equal to n, the right-hand side, the rightmost equation, expression, the integral becomes capital T. So the infinite summation disappears into one value when k is equal to n. And from here, it gives me an is equal to 1 over capital T, integral from 0 to capital T, or it may be a shifted version of that integral limits, x of t e to the minus j n omega 0 t dt. Now, finally, of course, this is the formula. We found an, the formula for an, but we were looking for a formula of ak, but just say that n is equal to k. So the formula that you will eventually need to remember is the following. AK is equal to, or CK, if you wish, that way, 0 to capital T, x of t e to the minus j k omega 0 t dt. This is the formula that you must hang on your wall, because it's the formula that gives the Fourier series coefficient value from the periodic signal x of t. By knowing the fundamental frequency is omega 0, and by changing k and putting into this integral formula, you will be able to find the different ck values. C1, for C1, for example, you have to substitute k is equal to 1. Take this integral. How are you going to take that integral? Well, it's your calculus skills, of course. If x of t is very complicated, sometimes this integral becomes very, very difficult. But for simple x of t's, they are pretty easy. So now we found it. We found the formula for the Fourier series coefficients. This is the Fourier series formula, and the expression of x of t using the Fourier series coefficients is, let me repeat it again, k from -infinity to infinity. We are calling it ak, e to the j k omega 0 t. And this is the formula for the signal using the Fourier series coefficients. So these twin equations are like the forward transformation and the inverse transformation. From xt, you can get AKs. Using AKs, you can get XTs. Okay. By the way, if k is equal to 0, when k is equal to 0, A0 is equal to 1 over capital T from 0 to t, x of t times e to the 0, which is 1, dt. And as you see, this is the average, or the DC value. So A0 is the DC value. A1, A2, etc., they are just harmonics. The strengths of the harmonics that we will be interested in. Now, clearly, we can do a lot of examples, and we will do that. For example, for simple x of t's, at least, it is possible to evaluate this integral for simple x of t. But for more complicated x of t's, we will see that we need something else. We need some shortcuts to inspect the answer, because this integral will become indefinitely more difficult. So we will use some properties of the Fourier series coefficients and we will deduce some results. We will usually not apply this formula for finding the Fourier series coefficients. For instance, if it is a cosine or a sine, we don't use this formula. Instead, we use the Euler's expansion, and from there, we can immediately find or observe the Fourier series coefficients. It's 1/2 or 1/2j for a cosine and sine, right? But for other shapes, we will have to use it at least for some simple shapes. And that simple shape is the box shape, by the way. We will start from that. There's the rectangular box pulse train with a half duty cycle, quarter duty cycle, up 0, rectangular box repetition. It is periodic, as you see. And for them, for those signals, this integral will be manageable. And perhaps that will be the only example of applying this formula for finding the Fourier series coefficients. For all the others, we will use different tricks, and we will almost never consult to this integration, but still, this integral is the formula for determining or obtaining Fourier series coefficients. So in an examination, if you are completely helpless, if you are desperate, you may have to do it. You may have to take this integral. I don't recommend. I recommend that you follow the courses and learn the tricks about how to find the Fourier series coefficients. But if you don't follow the courses, you will have to perhaps take this integral, and that will be difficult. Okay, so I will stop at this point, but first let me ask you if you have any questions. Is that clear up to now? Seems like no questions. All right, so next week is not the exam week, right? The exam week is 1 week after that. Am I right? Or am I wrong? Or let me discuss it after we finish this recording. I'll stop the recording.